So we've got a really cool exam here. This is the second exam of differential equations, and that deals with the matrices part of it. So in other words, systems of equations. This is from spring 2025, great vintage, lots of fun stuff ahead. Now, before we dive into the test, I do want to point out that the formula sheet doesn't have a lot that deals with systems of equations, but what it has is really useful. So that is fundamental matrices formulas. So make sure you have this handy because they might be fundamental to us doing well on the exam, right? Yes. All right, so know what these are, know when to use them. So we'll have these handy so that we can pull them out at just the right time. And also, before we begin, we want to make sure we put our name, because if we don't put our name, we're not going to get the credit. So full name, legibly, solution, J. Solutionson. All right, and with that, let's begin. Number 1. Use the substitution or elimination, and elimination is using that D notation, method to solve the following system of equations. All right, so we can do it in two different ways. Let's start with one, and then we'll see how we're feeling, whether or not we want to do a second way. So we'll go ahead and start with substitution. Now, the idea of substitution, if you think back to your college algebra days, those were good days. Well, the idea was to say, I'm going to solve for a variable in one of the equations and put that into the other. Now, we have to be a little bit careful here because there are sort of three things going around. There's the x, the y, the t. Now, t is the independent variable, so we don't want to solve for t. So in other words, we're thinking here as x is a function of t and y is a function of t. So we really want to get y by itself in terms of other things, or x by itself in terms of other things. So we actually get two choices here. We can do it either way. You'll notice in the first equation, if we were to rewrite it, we could solve for y. Now, you might say, couldn't you solve for x prime? You can, but usually it's better to solve for the things without a derivative, because that makes the final step a little bit easier. So that would say y is t minus x prime. Or if we came here, we swapped, we would say, look, x is y prime plus t, right? These are both true statements. All we've done is move things around. But now, what does this do? It says we can replace y by things that don't involve y, or we can replace x by things that don't involve x. So we can choose. And it doesn't really matter at this stage which one we pick. So let's suppose I like the one without a minus sign. Okay, so what can we do? So here, this came from the second equation, so I'm going to plug it into the first equation. So we say, all right, y prime plus t prime. Right? So this is not to the first, but the derivative. Know what you write, plus y equals t. Or, taking the derivative, y double prime plus 1 plus y is equal to t. All right. Aha. Success. Well, of a sort. Now, if you rearrange this, we say, or y double prime plus y is equal to t minus 1. So what we've done is we've gone from two equations with two unknown functions to one equation. And but we had to make a trade-off. The trade-off was originally we started with first derivatives. Now we have a second derivative. And that's essentially the trade-off that we make. Sure, fewer equations, but more derivatives. All right. Well, now we need to solve. And what do we see? Well, this is a non-homogeneous second-order differential equation. All right, no worries. We're amongst friends here, so we can do this. Okay, so what would we do? Well, we'd solve the homogeneous part, and we say, all right, that would be y double prime plus y equals 0. Turn it into an algebra problem, r squared plus 1 equals 0. and we say, this is going to get complex. Well, no, we have complex roots. R is plus minus I. So what that tells us is that the homogeneous system looks like some constant c cosine of t plus some constant d sine t. Now that's just for the homogeneous part. Then we come over here and say, okay, but wait, we're not done yet. Because what we need to do is do the non-homogeneous part. Well, we say, what does our non-homogeneous part look like? It looks like something that might come out of a homogeneous system, so that's good. So we can use method of undetermined coefficients. So in other words, we can pretend like we knew our answer up to some unknown values. And we say, well, those functions that we see are 1 and t. They don't overlap with cosine and sine. So we would guess for the particular solution, y sub p, well, it would look like some constant plus some constant times t. Well, take two derivatives, because we have to plug it into here, yp prime, and that's b, and yp double prime is 0. So now when we plug in the 0 for y double prime and the a plus bt in for yp, we get to the part where it says, look, we need a plus bt. I'll go ahead and put 0 plus, right? So this is y double prime plus y is equal to t minus 1. You say, well, what choices of a and b make this work? And the answer is, you set b equals 1, right? We're just comparing coefficients of t, and a equals minus 1. So our particular solution is, really, it's just that part right there. Now, we won't always be that lucky, but take it when you can get it. All right, so let's tie this all together. We reduced to one differential equation for y. We solved that for the homogeneous part, the non-homogeneous part. Now we can put it all together and say, hey, what's going on? And I should have labeled this, by the way, as YC, the complementary part, or the solution to the homogeneous part. So y, which is the sum of these two, becomes c cosine t plus d sine t plus, up here, t minus 1. Now, we're not done yet, because we need to solve the system, which means we need to have y and x. Okay, so how do we get x? All the way back to our substitution. That's why we want to solve for x, not for x prime. So, since we have x here, we say, well, look, x, it's y prime plus t. But wouldn't you know it, we happen to have y here. And so we can say, well, what is y prime? Take the derivative. Minus c sine t plus d cosine t, and then plus the derivative of this would be 1. Right, derivative of t is 1. So here's the y prime part, and then plus t. So rewriting it, we get x equals minus c sine t plus d cosine t plus, and I'll write it as t plus 1, and y equals c cosine t plus d sine t, and then plus t minus 1. And there we go. Because we don't have initial values, we can't solve for c and d. That's the answer. Now, you can check your answer, as we often should, by saying, well, what happens if you had x prime plus y? Well, if you take x prime, you'll see you'll get minus c cosine t, then plus c cosine t, 0. You get minus d sine t plus d sine t, 0. Then here you get a plus 1, and there's a minus 1. That's 0. That goes away. All that's left is t. So it satisfies the first equation, and then in a similar way, it will satisfy the second. Now, that's substitution. What if we wanted to do elimination? Do we have enough time? Well, I think since we always have time, right? You only have to do one. So let's talk elimination. Let's see if we can at least start down the path. And we'll just point out where we get similarities and where we get differences. So for elimination, so we're starting here. So all this up here, this part was the idea of substitution. What we can do is we can rewrite this expression. We have all the x's and y's are all on the same side, right? We move them all over. And so we say, look, this is really dx plus y equals t. And I'm going to rewrite this as minus x plus dy equals minus t. Okay? So I move everything over and rearrange. So, x is first, y is second. Now, with that in mind, what can we do? Well, we write this as a matrix. D1 minus 1d and then times xy equals t minus t. And we're going to do a little bit of Cramer's rule. Not exactly Cramer's rule, but basically Cramer's rule. Okay, so how does it work? Pick a variable. Doesn't matter which one, x or y. Let's pick y. And just so we can compare where we get to. So Cramer's rule says you're going to take the determinant, which we'll denote with this bar, and we have this d1 minus 1d, and then we're going to multiply that by y, and then that's going to be equal to the determinant, except we're going to do a switch. This part right here, the right-hand side, becomes one of the columns. It becomes the column associated with the variable we're solving for. We're solving for y, and if you look at our columns, well, we have an x column and a y column. So we're going to replace the y column because of the y. So we still have the d minus 1, t minus t. Well, over here, we'd have d squared and minus 1, that's d squared plus 1 times y. And on this side, we have d times minus t, and that's minus 1. That way, right? D, take derivative of that. Subtract minus t. So subtract minus t. Or if you rewrite this, this becomes y double prime plus y is equal to t minus 1. Now, I want to point something out. That's what we had up here. From this point, the rest of it's the same. It's like, hey, now that you have an equation with just one, solve it using the techniques you already know. And once you have that one, then you shouldn't do elimination a second time because that actually complicates things more than it helps. Just say, all right, pick one of the equations and solve for the other variable. Now find a place you can solve for x and plug it in. So the only difference between substitution and elimination is how do you get to that first step? Then from there, it's all smooth sailing. All right, so that's number one. All right, well, I guess we should make a note and do the same as before, just so we remember. Just so we remember. And with that, we bid adieu to number one. And we say, hello, number two. Rewrite the equation x4. Now, notice the 4 here is in parentheses, so we're not raising it to the power 4. That means 4 derivatives, plus 3x double prime plus x is equal to e to the t sine of 2t as a system of first-order differential equations. They didn't give us a lot of space, so there's probably not a lot of work to do. Now, here's the key. Do you see how we have fourth derivative involved? That means we're going to get 4 equations, okay? And the idea is essentially we're going to step up to the fourth derivative so that we're going to get to the point where we'll have an x1, x2, x3, x4. And every one of them is building up to a higher derivative. So we begin with the x1. And we say that's just going to be x. Now, x2 is the derivative of the previous one. But the key here is that's the same as x prime. So notice x1 prime is x prime, the first derivative. x3 is the derivative of x2. Now, what is x2? x2 is x prime, so that gives us x double prime. So see how this 2 matches with the number of primes? Not a coinky dinky. That's meant to happen. Now, x4. What is that? That's x3 prime, right? We want the derivative of the previous one. What is x3? X double prime. So this is x prime prime prime. So notice this 3 here matches that number of derivatives there. So we're going to stop introducing variables because we only want to go up to degree 4. That means we need 4 things. But we're going to make a note. What is x4 prime? Well, that is taking the derivative x prime 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 prime, or x, what we've been calling 4. Now that's the introduction of our variables. Now, we're going to do one other thing, and then we'll put our answer down. We're going to solve for our highest derivative. So x4 is minus 3x prime prime minus x plus e to the t sine 2t. All right, so just isolate that highest one. And now we're ready to begin. So most of our equations come from our ladder up. In fact, the majority of our equations come from the ladder, and then this equation gives us our last piece. So those are where our equations are. We just need to translate them and write them up. So we start. x1 prime equals x2. x2 prime equals x3. x3 prime equals x4. And what about x4 prime? Well, x4 prime, that's here. That's where we get our last equation. That is minus 3. What is x double prime? That's x double prime is x3, right? So x3. We don't want any derivatives here. We just want these pieces, x1 through x3. Minus x. What is x? That's x1. This e to the t sine 2t remains e to the t sine 2t. So that is the answer to part A. Now, one thing that we may have been asked to do is to write this in terms of a matrix. This one did not ask us to do that, but be ready. You never know. Now, part B. Rewrite the system x prime equals minus y, y prime equals 10x minus 7y as a single higher order equation, and use this equation to find the general solution of the system. Now you might say, whoa, wait a second. Didn't we just do that? Yes, we just did that on the previous problem. But I guess we'll do it again. Okay, it's the technique so nice. We'll do it twice. So how do we proceed? Well, there's a couple of ways we can go about this. One way is we can say, do we want to do, say, a substitution? Another way we can proceed is doing the D. What we talked about before, elimination. Which way gives us the right answer? Well, they both do. And here, maybe since it's so clean, see how it's like x prime and y? Let's go ahead and write that. We're going to say, look, this says that y is minus x prime. So I'm going to use that and put in everywhere where I see a y, I can now rewrite it using it as x. So I'm going to start with this y prime equals 10x minus 7y. And then this will become y, remember, is minus x prime equals 10x. I like the x, minus 7 times minus x prime. Well, what do we get? Well, that becomes minus x double prime equals 10x plus 7x prime. And we can move stuff around. We can move the x double prime over, rearrange it so it looks a little bit cleaner. In other words, x double prime, then x prime, then x. And we get x double prime plus 7x prime plus 10x equals 0. Cool. Cool, cool, cool. Now, I should pause and note that we sort of drove right past something that should have been boxed. We want to rewrite this as a single higher order equation, and that's right here. We could even have stopped right there. So here is our single higher order equation. So that's cool, but really we have to focus most of our energy on that single higher order equation. Hello, my friend. Now, let's, that's a lot of words. Okay, I'm going to move this up a little bit. We have plenty of real estate to finish the problem. No worries. No worries. We're doing great. Now, how do we proceed? Well, we know how to solve this kind. This is our nicest kind, right? It's homogeneous. There's a 0 on the other side. It's constant coefficient. It's linear. It has all the nice words. This is the ones that, if we were to take a differential equation home to meet the family, this is the kind that we would take home. We'd say, Mom, Dad, I met such a nice differential equation at college. I hope you like them. So we're going to first turn this into algebra, right? So polynomial r squared plus 7r plus 10 equals 0. Now, you have to remember, we're not giving you calculators, so something nice has to happen. In other words, it's got to factor nicely or has nice complex roots. And if it doesn't, that's a great time for you to pause and walk it back and say, hold on, did I miss something? But this time, it does factor. It's like they want us to succeed because they do. That's so typical of our math teachers. We're just like, hey, we want you to succeed. And oh, thank you. That's awesome of you. Notice we get r squared. Then we have 5r plus 2r, 7r, and plus 10. So that leads us to r is minus 2 and minus 5. Which tells us what? Well, now we translate that into solutions. So we say, well, x is some constant c e to the minus 2t plus some constant d e to the minus 5t. And I say, okay, so we've solved for x. We also need to solve for y. But now we say, well, y is minus x prime. So that's minus times, now take the derivative. Derivative of c e to the minus 2t minus 2c e to the minus 2t. Derivative of d e to the minus 5t minus 5d e to the minus 5t. Or that's 2c, right, because I can distribute the minus through, 2c e to the minus 2t plus 5d e to the minus 5t. So our final answer, we rewrite c, which we already found, c e to the minus 2t plus d e to the minus 5t, and y is 2c e to the minus 2t plus 5d e to the minus 5t. And there we go. That's our solution. Now we can check, what can we say? Well, y prime is 10x minus 7y. So we can say, well, take y prime. We'd have a minus 4c. And then we just say, okay, if I take 10 times this, well, that's 10c. And minus 7 times that, that's minus 14c. So that is minus 4c. Here, we have a minus 25d. Well, if we took 10 of these and subtracted 35 of those, right, because it's minus 7, you get minus 25. So you can check to see if your final answer is right by saying, let me just look at the original system and does it work? Because if it doesn't work, whoops, mistakes were made. We have time. Let's check ourselves before we wreck ourselves, right? We want the points. We want all the points. All right, so that's number 2. We finished it. This is our general solution. General solution needs to have both x and y. Notice something else. When you have your general solution, the constants you use for x need to show up in the constants used for y and vice versa. So if you see c's and d's, there's going to be c's and d's down in the other one as well. You can't say, oh, there's a bunch of constants here and a bunch of constants there. It's like, no. You got to see how they all fit together. All right, we're doing great. We're on pace. Beautiful. Catch a quick breath and on to number 3. Consider the system t squared x prime. All right, interesting. Equals t 2t squared 2 minus 3tx and t greater than 0. I'm going to make a note of that. Who knows if it's important, but whenever it's something a little bit different, I like to make a note of things. All right, so we have our setup. Now, what do we do? What do we do? Well, all right, what we can do is start part A, right? Start there. Show that x1, which is this solution, 2t squared t, and x2 minus t to the minus 3, 2t to the minus 4, are solutions to the system. So what do we do to show something's a solution? Well, we literally plug it in. So let's start with x1. So we're going to look at t squared x, t squared. I don't know why I made a subscript. Excuse me. T squared x1 prime. Got to be careful. Some things are upstairs, some things are downstairs. Make sure you put things in the right place. So that's t squared. And the way you take a derivative of a vector is take the derivative of each entry. Derivative of 2t squared, 4t. Derivative of t, 1. And now, if you multiply that, t squared times 4t is 4t cubed. T squared times 1 is t squared. All right, so that's left-hand side. Now, right-hand side. We're going to take t, 2t squared, 2 minus 3t times x1. So this is our x1 here. Well, that is 2t cubed plus 2t cubed. Then it's 4t squared minus 3t squared, which is 4t cubed and t squared. And the key here is they match. If they match, that's a solution. And that's the verification. Now, unfortunately for us, we've got to do the same thing a second time with the space we have left. All right, I think we maybe have just enough space to pull this off. So, how do you verify? You plug it into both sides and check, does equality hold? So, here we go. T squared x2 prime. Well, that's t squared. Take the derivative. So, minus in the exponents, same rules as if positives are in the exponents. You bring it down, subtract 1. So the minus 3 comes down. That becomes a positive 3, t minus 4. The minus 4 comes down, that's a minus 8. Subtract 1, t minus 5. Put the t squared inside. That becomes 3, t to the minus 2. And minus 8, t to the minus 3. Okay. That's the left-hand side. Now, we'll do the same thing where we check the right-hand side. So we have our t, 2t squared, 2 minus 3t, times x2 minus t to the minus 3, 2t to the minus 4. This is our x2. Well, that is t times minus t to the minus 3 minus t to the minus 2. Then 2t squared times 2t to the minus 4 plus 4t to the minus 2. Then 2 times minus t to the minus 3 is minus 2t to the minus 3. Minus 3t times 2t to the 4 minus 6t to negative 3. We put those together, we get minus and minus 1 and plus 4 makes a 3. T to the minus 2, because the t to the minus 2 is matched. T to the minus 3 is matched. Minus 2 minus 6 is minus 8. And what do we see? Again, they match. So, since they match, they are solutions. That's the computation we're looking for. All right, next one. Part B. Find the Wronskian. Okay, simplify it and explain why the two solutions are linearly independent. Well, how do you find the Wronskian? Well, the Wronskian, now you have to remember there's sort of two flavors of the Wronskian. There's the flavor of when you have a high degree single variable, and then there's the flavor for systems. Now for systems, what you do is you're going to make a determinant of a matrix, and the columns are your solution. So you're going to make a column for each solution. In this case, we have two solutions, two columns. So we say, okay, here's x1. So we put that in, 2t squared t. Here's x2. That's in our other column. Minus t to the minus 3, 2t to the minus 4. Now we're going to take this as a determinant. That's why I put straight lines, not the parentheses. Because it's not the matrix, right? That's parentheses. It's the determinant of that matrix. Well, so we go down the diagonal. That would make it a 4. T squared times t minus 4 makes 4. T to the minus 2. Subtract, going up this diagonal. Well, that's, again, t to the minus 2, but there's a minus. So we're subtracting a minus t to the minus 2, which is 5. T to the minus 2, or if you like, that's the same as 5 over t squared. Now, what are we looking for? We want the Wronskian to not be 0 and not be undefined. You might say, but what about 0? Do you remember how we said we should underline this? This might be important because it's important. See, this t greater than 0 is going to help with that. So we say, now, here's the key. So this is part of our answer. This is the Wronskian, right? They asked us to find the Wronskian. We did it. We simplified it. Yes, we did that. Now, this is for t greater than 0. This is defined and not 0. So, linearly independent. So, if they want an explanation, that's the key. Essentially, linear dependence, whoops, I ran out of space. Linear dependence means that you have repetition. Repetition means that you have 0 in the determinant. Repeated rows or repeated columns or some combination that causes repetition. So as long as it's non-zero, you're good to go. Essentially, if for all you linear algebra fans out there, because it's non-zero, what it means is that you can combine to get anything. Every possible combination is on the menu. And that's what you really are looking for. That says, hey, I can solve anything. So, all right, that's B. Now, part C. Write the general form for solutions to the system. Well, it's linear. You might say, well, wait, is it linear? There's a whole bunch of t's here. It's still linear, right? The linear is looking at how the x prime and the x are in. This is a linear system. It's linear. It's homogeneous. It's not constant coefficient, but that doesn't matter. But because it's linear, what can we do? Superposition. What does superposition mean? It just says if you have two linearly independent solutions, then any combination of them is still a solution. And then we say, oh, wait, looking at the size, that gets all the solutions because it's a 2 by 2. So what does part C look like? Part C is 3 points, right? They didn't mark down how much part C is worth, but it looks like x is some constant times x1 plus some other constant times x2. And that's the general form for the system, right? So here's your x1 and here's your x2. So that's the kind of question we like. Even if we got A wrong, even if we got B wrong, we're still going to get C, right? Because it says, hey, you gave me x1, x2, superposition, and I'm just feeling super, right? Yes, yes. Okay, let's keep moving. Number 4. Consider the system. X prime equals AX, where A is this matrix. 2 minus 3, 3, 2. Find e to the AT. And boy, they gave us a lot of space. Okay, so here we have to remember that there are sort of 3 possibilities. And they all based on what are the eigenvalues of A. So we're going to do a quick refresher. We'll just do this once. We might see a similar problem. I don't know what the next one says, but let's just remember. If we have repeated roots, okay, in other words, the eigenvalues are the same, then formula sheet. They might say, wait, what? What does that mean? Here's the formula sheet. Do you see this one right here? This e to the AT is e to the lambda t, I plus t, a minus lambda I. That's repeated roots. Okay, well, that's good, because there's only 3 things that can happen, and so the formula sheet carries the day for one of them. You might have complex roots. In other words, A might show up. Now, for this one, now what do you do? The answer is formula sheet. You might say, wait, what? The formula sheet again? Yes. Yes, this very big one here. That's the formula sheet. And this deals with the complex case. Complex, you can see, because you get the sines and the cosines. Now here, alpha is the real part of the complex roots. Beta is the imaginary part of the complex root. But then you just plug it in and carry it out. So you say, okay, good. But what if they're distinct real? Now, that's the third case. Distinct real roots. Well, then we have to do 2 things. We have a little bit of elbow grease and the formula sheet. And like, wait, what? Well, because what's e to the AT? E to the AT is the fundamental matrix. It's like the best one. So what we can do is we do a little bit of elbow grease to find phi of t, which is a fundamental matrix. And then we use this fact here to find the fundamental matrix. So if you have anything which asks for e to the AT, this is your friend. You want to use this. Okay, now the elbow grease is finding your eigenvectors. That's the elbow grease. Now, I don't know which situation we're in right now. Let's find out. So here we go. We're going to take a minus lambda I and take that 2 by 2 determinant. 2 by 2 because this is 2 by 2. So that's the determinant of 2 minus lambda minus 3, 3, 2 minus lambda. Well, that becomes 2 minus lambda quantity squared subtract, well, minus 9. And, well, okay, this is lambda minus 2 squared, because if you put the negative through, it doesn't make any difference, plus 9. And we set this equal to 0. And now we can actually, because this is repeated, we don't expand, we can just solve, right? Move the 9 across, and we get lambda minus 2 quantity squared equals minus 9, or lambda minus 2, take the square root, You say, but there's negatives. Yes, things are going to get complex. So plus minus 3i. And lambda equals 2 plus minus 3i. All right, so now we know our plan. We're going to be using the formula sheet. So here is our alpha. Here is our beta. So let me write down the formula from the formula sheet. And this one's the long one, right? Because, well, it's the most complex one, so it's not so surprising. E to the AT is e to the alpha t cosine beta t times the identity matrix plus 1 over beta e to the alpha t sine beta t times a minus alpha times the identity. All right, so I'm just copying right from the formula sheet. So we now have our pieces. We found our roots with our complex roots. The alpha is the real part, the beta is the imaginary part. So alpha is, let me be clear when I say what alpha and beta are. Alpha is 2. Beta is the 3. Don't worry about the plus minus. It's the 3. Now we put this together. We get E alpha, okay, so that's E 2t, cosine beta, cosine 3t, times the identity, 1, 0, 0, 1, plus 1 over beta, 1/3, e to the alpha, t, e to the 2t, sine beta t, sine 3t, times a, and here's our a, so it's going to be 2 minus 3, 3, 2, subtract alpha 2 times the identity. And that's 1, 0, 0, 1. That's what I means. Now here, if we just carry out this computation, well, we get 2 minus 2 makes 0, minus 3 subtract 0, minus 3, 3 subtract 0 is 3, 2 subtract 2 is 0. And notice there's a 1/3 there. So this becomes, we have e to the 2t cosine 3t, 1, 0, 0, 1. The 1/3 multiplying in, we get e to the 2t sine 3t times 0 minus 1, 1, 0. And so now we just multiply in and add. So this gives us e to the 2t cosine 3t plus 0, 0 minus e to the 2t sine 3t, so minus e to the 2t sine 3t, 0 plus e to the 2t sine 3t, then e to the 2t cosine 3t, plus 0. So there we go. Now, do you have to use the formula sheet? No. But would it be foolish not to? Yes. You can do this another way. So the other way to do this is once you have your complex eigenvalues, find your complex eigenvector, and then you do, right, okay, e to the a alpha plus beta I times my complex eigenvector. You sort of expand it out. You find your pieces, which gives you your fundamental solutions, it gives you a fundamental matrix, and then from the fundamental matrix, you get the e to the at. It's a lot of work. The formula sheet makes it all built in, so it's all automatic. Take advantage. Take advantage. All right, now we're not done because there's a part B. So let's finish part B. Solve x prime equals ax with x of 0 equals 1 minus 1. Now, here's the thing, is once you have the fundamental matrix, this is an easy solution Because if this is what you're given, x prime equals ax with x of 0 equals 1 minus 1, the solution always looks the same. It's x is equal to e to the at times x0. All right, that's it. So if you ask solve x prime equals ax with some initial condition, there's your solution. So what do you need? Well, you need e to the at, which we have. You need x0, which is given. And then you're like, cool. So I just have to put all those pieces in and multiply, and we're done. Yes. Yes. Exactly. See, some things are meant to be hard, but some things are not. Don't make things hard if they don't have to be. So I'm copying down e to the at. So here's my e to the at. It's a lovely looking expression. Sorry, it's a lovely looking expression. Excuse me. Now I'm going to copy down my x0. 1 minus 1. And now carry out the matrix multiplication, right? This is a 2 by 2 matrix. We're going to end up with a vector. So e to the 2t cosine 3t, and then we're going to have minus 1 times that minus. So we get in the first slot e to the 2t cosine 3t plus e to the 2t sine 3t. Then in the next slot, e to the 2t sine 3t minus e to the 2t cosine 3t. And there's the answer. Kapla! Which, as we all know, is Klingon for success, right? Yeah, this looks intimidating, but if you know how to use the formula sheet to get e to the at, and know that once you have e to the at, that you can solve initial conditions for systems really quickly, life is good. Life is wonderful. All right, well, still 2 problems left. Let's finish it. Okay. Number 5. Find the general solution. So we have x1 prime equals 3x1 plus 4x2. x2 prime equals 3x1 plus 2x2. All right. Well, for this one, what can we do? We can go back and use the D kind of arguments, things we were talking about at the very beginning. That's perfectly valid. We can do substitution. That works. I like matrix techniques because matrix techniques makes things work really well. Okay, so how does that help us? So let's go through and talk about this. First off, we're going to transform this into a matrix. So we're going to think of this as x1, x2 prime is equal to, and read off our coefficients, 3, 4, 3, 2 times x1, x2. Now, we're going to come and ask the question, what can we say about those eigenvalues? Well, let's take a look. Here we go. This computation, you'll do it a lot, so you should get really comfortable with it. We're taking 3 minus lambda, 4, 3, 2 minus lambda. So this is our, a minus lambda I determinant. All right. Well, this becomes 3 minus lambda times 2 minus lambda, subtract 3 times 4. Well, this is a case where we should distribute. Now, previously, because these were the same, it didn't make sense to distribute, but here we should. So that would give us our 6. And then we have a minus 3 lambda minus 2 lambda makes a minus 5 lambda plus a lambda squared and minus 12, or lambda squared minus 5 lambda. 6 minus 12 is minus 6. If we lived a good, clean algebra life, this should factor. Well, it does. Lambda minus 6, lambda plus 1. Right? Lambda squared plus lambda, minus 6 lambda, minus 6 lambda, and then minus 6. All right, now, these are distinct roots. Okay, cool. So, what do we do next? Well, now, if we have the distinct roots situation, so we get two roots, distinct real roots, I should say, then what we're going to do is we're going to find eigenvectors. Okay, so now we're going to do eigenvectors. I'll shorten this as just E vectors. Then it says like, oh, this is like, very tech savvy. There's an E. Wow. Back in the day, you just threw an E in front of a name, made a website, boom, millionaire. Unfortunately, I'm pretty sure E vectors has already been spoken for, so I guess I'll just have to keep teaching math. All right, so we have lambda equals 6. So we're going to take A subtract 6i. So see where that lambda is? We're going to put that in. So we can actually just refer to it here. Minus 3, 4, 3, minus 4. I'm looking for something to multiply this by that gets out 0, 0. Now, there's lots of ways to find it. Here's what I like to do. Pick a row, any row, doesn't matter. Let's say I pick the first row. So I'm just going to write it backwards. And then I flip the sign of something. I'll flip the sign of the negative. My claim is 4, 3 does it. Let's check. Minus 12 plus 12, 12 minus 12. Aha! Success! We did it! You can always, verify that something's worked. You can even come back to the original. Like you have 12 plus 12 makes 24. That's 6 times 4. 12 plus 6 is 18. And that's 3 times 6. So, works. Okay, so this is good. Now, here's what we do. We combine the eigenvector with eigenvalue. And so, we get this 4, 3 eigenvector, and then we have e to 6t. We oftentimes put it in the function in the front. So e eigenvalue t times eigenvector. Okay, so this is a solution. All right, keep that in mind. We're going to come back to that. Now, we're going to do this again. Round 2, because we're going to do it with lambda equals minus 1. All right, so we're going to take 3 minus minus 1. That's 4. 4. 3. 2 minus minus 1. 3. And then, okay, we just, again, pick a row. Doesn't matter. I can pick the second row this time. 3, 3. Change the sign of one tree. And that's going to work. Let's check. 12 minus 12, 0. 9 minus 9, 0. Now, we can stick with this. There's nothing wrong with it. But we can always scale. Scaling is always an option. So scaling by a non-zero is okay. So I tend to like to scale. So I'm going to go ahead and scale by a third. So what does that give us? Well, it says, hey, e to the minus t, sorry, that's minus 1 times t, times 1 minus 1. That was the scaled version. That's a solution. Now here's the cool thing. We've now found two solutions. Because they came from distinct eigenvalues, they're guaranteed to be linearly independent. And at this point, we're like, cool. So we can take linear combinations. So our solutions to the matrix form of our setup, what does it look like? Well, we have our x1, x2. Looks like some constant c. It doesn't matter which order you go in. I'll do it in the order we solve. E6t, 4, 3, plus some constant d, e minus t, 1 minus 1. Now, if we stopped here, we wouldn't get all the points. We want all the points. Let me just talk about why. We introduced this matrix notation. The problem didn't give it to us. So we convert it into that matrix form. So at the end, we have to pull it back. But that's not hard. Because what's going on. We can just say, look, let's just push this all into one vector. So this would be the vector, multiplying this in, 4c e to the 6t, and then plus d e to the minus t. Downstairs, 3c e to the 6t minus d e to the minus t. And remember, this is still x1, x2. And now we're like, hey, whoa, hold on a second. I just read across. The first entry is x1. The second entry is x2. So our solution is x1 is 4c e to the 6t plus d e to the minus t. And x2 is 3c e to the 6t minus d e to the minus t. Huzzah! It works. It works. And it's all nice and clean. So, matrices actually are a powerful ally. And once you get the hang of them, they'll get you through a lot of good stuff. All right, that's number 5, which means we're near the end. And our last one is number 6. Find 2 linearly independent solutions of the system x prime equals ax, where a equals 2 minus 1, 1, 0, okay? And then write a fundamental matrix for the given system. All right, now, here's the thing. We don't have to do it in the order they asked. We can start with the fundamental matrix and go to the 2 linearly independent solutions. And when I see A, I think I should try to get fundamental matrix. So the first thing is we're going to look at the eigenvalues. So here we go. We're going to take the determinant of A minus lambda I. So that's going to be a determinant 2 minus lambda minus 1, 1 minus lambda. So do our multiplication, 2 minus lambda times minus lambda. Don't forget these minus signs. They're important. Be careful. No need to rush. Minus 1. Okay, so that becomes lambda squared, right? Minus lambda times minus lambda, minus 2 lambda plus 1. Which to the knowing observer, you'll say like, ooh, that's lambda minus 1 squared. Now we set that equal to 0, and what do we see? Repeated eigenvalues. 1, 1. Okay. So we are in the repeated eigenvalue case. Now, you probably should not be surprised if you see, right, there are 3 situations we could have been in: complex, distinct, real, repeated. I'd bet you at least 2 out of the 3 you'd see on any exam for this part of the course, and sometimes all 3. So this is a case we're going to see all 3. So let's look at our formula sheet, and notice we have this part right here. So I'm going to rewrite it. That's e to the at. So e to the at is equal to e to the lambda t. All right. I'll write that, e lambda t, times the identity matrix plus t times a minus lambda I. Okay, so I'm just copying it down. All right, we'll put that aside. That's our last time we visit the formula sheet, because this is our last problem, right? Now, we just have to figure out how to put this all together. Lambda is 1. All right, I agree. So this becomes e to the t times 1, 0, 0, 1 plus t times a minus 1 times I. Okay, so it's like you come here. This is your a minus lambda I, but now you put in lambda equals 1. So that's 1 minus 1, 1 minus 1. Which is e to the t times, and we'll just put these together. So we're going to get 1 plus t times 1, so that's 1 plus t. 0 plus t times minus 1, that's minus t. 0 plus t times 1, t. 1 plus t times minus 1, 1 minus t. And we can even go one step further and say, well, we can put the e to the t in. And I'm doing this for a very specific reason, because we'll see why in just a second. So this is 1 plus t, e to the t, t, e to the t, minus t, e to the t, and 1 minus t, e to the t. All right, so this is e to the at. We've said it before, but you know what? We're going to say it again. And not only are we going to say it, we're going to write it. This is the fundamental matrix. In fact, it's the fundamental matrix. So of all the fundamental matrices, because they're not unique, this is the best one. You might say, okay, yeah, that's great. But what does that have to do with anything? Well, what does a fundamental matrix consist of? The columns are solutions. All right. So that says, hey, not only are they solutions, they're linearly independent solutions. We have defined linearly independent solutions. So 2 things. 1, this is part of the answer. This is the fundamental matrix. Now, they're very sneaky. They said, write a fundamental matrix. We did it in reverse order. We found the fundamental matrix. We still have to do the first part. What are 2 linearly independent solutions? Now, we say, okay, grab the columns. Those are your linearly independent solutions. So, just writing the columns down. These are our 2 linearly independent solutions. So whenever you have a fundamental matrix, the columns make up a set of linearly independent solutions. And so, in particular, a linearly independent set of solutions for the x prime equals ax. So we found e to the at. We had the formula, so it's really quick. Didn't have to work too hard. And then we said, hey, now that we have that, pull down the columns, because we understand that this is fundamental. We know what that means, and we use that to our advantage. So by knowing what things mean, we save ourselves a lot of work. And it turns out now these problems don't have to be scary at all. In fact, they're straightforward. They want us to succeed because we do want you to succeed. Please, please do well on the test. I have been a grader for many, many years. We love it when you get a high score. It's so much better to grade. So please do well. We want you to succeed. And you're capable of success. We believe in you. We're invested in you. So invest in yourself because you are worth it. Thank you so much for putting in the time, putting in the practice. All these hours are ready to pay off. You can do this. Go for it. Be great. All right. Good luck. Bye.